Okay, so I think everyone in this audience agrees that dark matter exists. And we know this from the dark matter's gravitational pull on stars, dark matter's gravitational imprints in the CMB fluctuations, and its imprints is gravitational imprints on the large-scale structure of the universe, and from gravitational lensing of dark matter by dark matter of galactic clusters, right? So, the possibility that I would like to discuss in this talk is, could gravity also help us pinpoint dark matter's microscopic identity? So all the evidence we collected about dark matter is through gravity, so could it do one more trick for us and help us actually solve the mystery of dark matter? Right? Okay. Now, one of the very few things we know about dark matter is that its mass, phenomenologically, from a phenomenological perspective, falls in this range, which spans about 90 orders of magnitude. Which I was hoping to say that with a straight face, but yeah. And for very good reasons, most efforts in model building of dark matter and experimental detection have focused on the 37 orders of magnitude in which we think dark matter could be a wave or a particle, right? But there are many, many orders of magnitude where dark matter is probably not a particle, but is some sort of macroscopic structure. And not much attention has been given to these orders. And there are two reasons for that. One is that it's just very hard to go look for these super heavy dark matter candidates. And the other is that it's very hard to guess what dark matter that is this heavy could be, right? That is, if you ask the question, how does dark matter ever become this heavy? You don't have many answers. A zeroth level answer that you would give is that, well, this could be black holes formed, say, in the very early universe through enhanced density perturbations or something, right? But primordial black holes is not going to be the focus of my talk. Now, I could rephrase this question as, what structures, macroscopic structures, could dark matter inhabit? Well, here's the matter power spectrum, the dimensionless matter power spectrum, to be more precise. On the x-axis is the inverse distance scale, which could also be couched in the language of the mass of the structures that you would form, the halo structures that you would form. Now, we know how the matter power, we have measured the matter power spectrum at cosmic scales, at the scales of galactic clusters, and at galactic scales, but we have very little empirical knowledge of what happens at scales smaller than that. Okay? Now, the cold dark matter paradigm predicts that the power in these very small scales is suppressed. And what that means is that if dark matter is some sort of a WIMP, then its population would be scarce in structures that are smaller than galactic halos. Most of the halos that we know about are galactic scale, is what it means. Okay? However, as these folks had shown, if you have an early period of matter domination near reheating stage, or if you produce a bunch of vector bosons at during inflation, then you alter standard cosmology, and that could lead to strong clustering of dark matter at very small scales and enhance power at these scales. And so in these scenarios, most of the dark matter, a large fraction of the dark matter, could actually be sitting in very big, in giant structures, but smaller than galactic halos. Okay? And then there are these quantum structures, like boson stars, for example, axion stars, in which the self-gravity of the star is balanced by a combination of the kinetic pressure of fields in the star or repulsive self-interactions in the star. And it's possible that dark matter most of the dark matter could be sitting in these microscopic structures. Okay, so all these are non-baryonic compact subhalo structures. Okay, that's one way to describe it. All right, so if dark matter were in these giant structures, then the best bet we have of finding them is through gravitational probes. And the first thing that would come to your mind would be gravitational waves. The gravitational waves that could be produced by binary mergers of these structures, or some sort of a transit in front of stars and other structures, and so on. So here's a recent white paper on all sorts of signatures, all sorts of gravitational wave signatures from all sorts of macroscopic structure candidates for dark matter. And I refer you to that vis-a-vis gravitational waves. One other neat gravitational probe for finding these dark matter structures is to make use of pulsar timing arrays. The idea is that if one of these structures passes in front of, passes in between us and one of these arrays of one of these pulsars in the pulsar timing array, then it could either accelerate the Earth, the dark matter structure, or accelerate the pulsar, and that would lead to changing in the timing that you measure in these arrays. Or it could just distort space-time, and that would make light come to you a little later from one of these pulsars, which gives you a handle on the microscopics of the structure. Okay. Now, a third possibility to probe these structures gravitationally is to use what is known as microlensing, and that's what I'm going to focus on. Okay, so the basic principle behind microlensing is that matter bends light, and this was posited first by Newton, although for the wrong reasons. Newton thought light was made of particles called corpuscles, which had mass, so he thought massive bodies do bend light. And then it was 100 years later, Cavendish and Solner actually worked out the deflection angle of light by a massive body. And they did think about being able to see an object behind the sun, and a star behind the sun at its apparent position, where that's the deflection angle. And they worked out that the deflection angle goes as the mass of the deflector divided by the impact parameter of light. Okay, so the more massive an object, the more you bend light, and then the farther away light is from the object, the less it bends out. All right, and 100 years after that, using just the equivalence principle, Albert Einstein was able to also derive the deflection angle to be this value. However, when he updated general relativity, well, the first realization was that matter does not bend light, it actually bends space, and light just follows along, right? So in the more general picture, when you derive what the deflection angle is, that actually comes out to be 2 times the old incorrect deflection angle that you get from the equivalence principle. So that's the key to this whole talk. Okay? All right. Now, one spectacular consequence of the fact that matter bends space and hence light is what is known as gravitational lensing. This is what you get when you have a source that is directly behind your lens, so that the light bends around in all directions around the source before it gets to you. As a consequence of which, you get a nice ring. The source is seen as a ring around the lens in front of you. Also, a ring that is known as the Einstein ring. Here's a picture of a blue galactic cluster that is lensed by some luminous red galaxy in front, producing a near perfect Einstein ring, because the alignment is nearly perfect. Okay. Now, a quibble I have about this phenomenon is that this is actually not lensing, because in a lens, the farther you are from the center of the lens, the more the deflection angle, so that you actually have a focal point. Here, there is no such focal point. Here, you are just the farther you are from the lens, the less that you deflect. So you don't have a focal point, you have some sort of focal line. It's just, I would just call it convergent deflection or something. It's not exactly lensing the way you would think about it. Okay? Now, this is what is known as strong lensing, the ability to see these images, these rings and arcs, is what is known as strong lensing. And this is not microlensing, and this is not going to be what I'm talking about. Because what microlensing means is you don't see the images. You look at some light source like a star, and all you see is a brightening of the star. You don't actually resolve the images. And also, strong lensing generally means this image just remains for a long time, whereas in microlensing, the magnification of the star or light source is transient. It could be for a few minutes, or it could be for a few months or years. And this could be caused by anything that passes in front of the star that you're staring at, be it a planet, or a neutron star, or a black hole, or whatever. Okay? And this is how, and we've used this method to actually discover like 11 exoplanets. This is one of the ways we discover exoplanets. Okay. So here's how a microlensing event would actually look like if you were able to resolve it. Let's see. So the empty circles track the position of the source. Sorry, the lens that you're looking at. And then the source is behind you. You may not even be able to see it. It could be that dim. And then as the lens passes in, as the lens transits in front of the source, so you get two images, and the images are collinear with the lens and the source. And these images sort of look like this. Okay, so as the lens passes in this direction, you start getting images from in this direction, and then an image in this direction. One contained within the what is known as the Einstein Radius, which I'll talk about in a moment, and one outside it. So a near image and a far image. Okay, so I could have shown this as an animation, but the only reason I showed this as a picture was to emphasize the collinearity of the images and the source and the lens. Okay, but I do have an animation as well that doesn't show the collinearity explicitly, and that's this. So that's the source. Sorry, that's the lens. Here's the source, and then you see the images moving around. Right. So that would have been what we could see if we are able to resolve the images. But what we actually see is a light curve. Right. What we actually see is is an amplification in the intensity as a function of time. And you could see the individual, the amplification of the individual images as well. Right? So if you see this light curve, that's your smoking for my curve. Okay. All right. So let's see how we can actually put this to use to constrain dark matter. And for that, let's try to understand the geometry of this whole microlensing process. So here's the observer separated from the lens by a distance, let's say dl, and here's the source separated from the lens by a distance dls. And then you put them together, that's the distance ds. So the light from the source, so okay. So now let's say you're looking at the lens, and then the light from the source gets deflected on either side of the lens, so that the observer would be able to see the source as these two images. Okay, and let's call the angle subtended by the source to be theta, and the angle subtended by the lens and the optic axis to be beta. That is the impact angle. Okay, so with this geometry, you could set up a very simple lensing equation. The lensing equation is just an addition of the distances on a source plane. That is, after you project the images onto a source plane, you just add up the distances, and what you get is a relation between the angle subtended by the source, angle subtended by the lens, and the deflection angle, right? And that relation is just use angles and distances to construct triangular distances, so that you get this as an equation. And the main thing I want to point out is that the angle subtended by the image comes to be something, a deflection angle, which also goes as 1 over the angle subtended by the image. Okay? Okay, so you have that. And that gives you a definition of what is known as an Einstein angle, which happens when the lens and the observer and the source are all aligned. Okay, so that when they're in a CCG, the impact parameter is 0. You get an Einstein angle, which is the angle subtended by the images, which is also the angle of closest approach of light. Right? And that gives you a definition of what is known as the Einstein Radius, which is the radius that you would see on the lensing plane using this angle subtended by the images. Okay, so that literally is the closest approach of photons to the lens. Okay. All right, so the lensing equation helps you define what an event is, because from the lensing equation you can get what the magnification is at a given point of time, and the magnification is nothing but so the solid angle subtended by the source onto you divided by the solid angle subtended by the images onto you divided by the solid angle subtended by the source. Because the magnification is nothing but the area of the images divided by the area of the source. Right? So with the lensing equation, you can derive what the magnification is. And for a given impact parameter u and a point-like lens, such as a primordial black hole, you find that so you find that this is the magnification in terms of the impact parameter. And then when the impact parameter is at the Einstein radius, the magnification turns out to be 1.34. Okay, so just when it is getting into the point of closest approach of light is when you get a magnification of 1.34. Now that defines what an event is in a microlensing survey. So an event is when, for a transit, the magnification goes above 1.34, that's your cutoff. So whenever you have an event with a magnification above 1.34, you call that an event and count it as an event for the clusters. Okay? All right. Okay, so that means, given this definition, we can now count the total number of events in a microlensing survey. And the way you count it is based on the fact that the telescope that you use is actually sensitive to only a small range of transit times. Okay? So that what you're actually doing is sampling the dark matter speed distribution, usually assumed to be Maxwell-Boltzmann. So that in the end, your event rate ends up, your event rate in terms of, as a function of the transit time, ends up looking like some sort of a Maxwell-Boltzmann distribution, right? Where you take into account the efficiency of detection, and then the density of dark matter along your line of sight to the source, and the circular speed of dark matter in the Maxwell-Boltzmann distribution, and you define some sort of a velocity for our dark matter transit through your Einstein radius, your lensing tube, so to speak, right? So what that means is, since you're actually sampling the Maxwell-Boltzmann distribution, if you're thinking about very heavy lenses, these are the lenses that have an Einstein radius that's very huge. That is the lensing tube through which you're looking at the whole event is so thick that you can only sample the slowest dark matter particles, right? Because if you're looking at faster dark matter particles, then they just zip through, so you don't find them. Whereas for very light lenses, given a range of transit times that you are sensitive to, the lensing tube is really thin, so that the only dark matter that you can actually sample is the very fast end of the speed distribution.
Not sure what you mean by tube here.
Okay, sorry. The tube is, I should have put something up in front. So the tube is basically, so the Einstein radius is not a constant in the distance to the source. It actually becomes thicker and then thins down. So this whole thing is the tube through which, an imaginary tube of Einstein radius through which you look at the source. Okay, so to count events, you actually rely on different parts of the Maxwell-Boson distribution. All right. Okay, so now with all this information, knowing what an event is and knowing how to count events, you could calculate event rates for an actual microlensing survey. The surveys that we are thinking about are the historic EROS survey, which looked at look for lensing events in the large Magellanic and small Magellanic clouds. And also the recent OGLE survey, which looked at the Milky Way bulge for a few years. Okay, and here's how the event distributions look in transit times for a few different masses. So OGLE was sensitive to transit times of 0.1 days to like 300 days. Like a year, whereas EROS was sensitive to 1 day to 1,000 days. So given that, for the lightest dark matter masses that you could think about in this range, so this is how you get. So these are the OGLE event rates, and these are the EROS event rates, and as you can see, some of these get cut off because they're not sensitive to transit time smaller than that, right? Whereas in somewhere in a mid-range, you are sensitive to the entire distribution in both surveys. And if dark matter is really heavy, then you only see the slowest part of dark matter. So again, you get cut off at high transit times. Okay.
So that's the rate of detection as a function of the transit time, is that it?
Yeah, that's what it is, yeah. So again, the idea is for light dark matter masses, the Einstein radius is so small that for the smallest times, most dark matter particles just zip through, so you can only sample the slowest dark matter. And here you only sample the fastest.
Are those sensitivities or detections?
No, this is just the detection rate per source star in units of per day, as in per transit time, per exposure time.
The expected rate.
This is the
detected
expected rate, yeah.
Not the detected. Okay.
This is actually also the detected rate. So these are surveys that have already been done.
Okay. So
Yeah.
you're going to use these as upper limits.
Yeah. Yep. You could turn this into an upper limit. Yep. And the upper limits are published. So yeah. Okay. So as I was just saying, you could turn this into limits on the population of primordial black holes and candidates known as MACHOs, massive compact halo objects. Basically, baryonic structures that are too dim to see, such as brown dwarfs, neutron stars, etc. And to actually turn them into constraints, you also need to know where the sources are, the Magellanic clouds and the bulge, so that you need to know the density profile as in the line of sight. And you need to know how many stars that you're looking at, and the total observation time, the total exposure of the experiment, and of course the range of transit times that you're sensitive to. So with all that information, you could turn the event rates that you calculate into bounds, and that's what these surveys did. And when I did them, when I did my recast, I mostly agreed with what OGLE was able to get, but I do disagree with the bound set by EROS. And that's because EROS didn't actually put in a Maxwell-Boltzmann distribution for the speeds. They just took sort of a Dirac delta distribution. They just put all the dark matter at 220 kilometers per second. That means I agree with them at intermediary masses, but not at low masses where I sample the small length, the small velocities of the dark matter distribution. Okay, so what do these constraints tell you? That if dark matter is in most of dark matter is in primordial black holes, then OGLE rules it out for mass ranges of 10 to the minus 7 to 10 to the minus 2 solar masses, up to fractions of like 1%. Okay, so if dark matter is in primordial black holes, it's probably less than 1% for in this mass range. And similarly, for EROS, again, the mass ranges that you constrain are between 10 to the minus 5 solar masses and like 10 solar masses, again, all the way down to 10 to the 1% in population. Okay? All right. So now we've learned how to define an event in microlensing, how to count events, and how to get constraints for point-like lenses, such as primordial black holes and MACHOs. But we just argued that dark matter could also exist in these macro fluffy substructures, such as like subhalos that are ultra compact, have some NFW profile, or they could be some sort of axion miniclusters, or boson stars, and so on. Right. So how do we constrain these objects with microlensing? Well, intuitively, we can guess that the size of this object should matter, right? Given a certain mass, how big how fluffy these objects are should actually matter, because if the lens was a small lens, and you could contain the lens in the entire lensing tube, then it should behave like a point-like object. A point-like lens, right? So its efficiency of lensing with respect to a point-like lens should be 1, right? However, if I make it a little fluffier, the same mass but larger size, there may be parts of the lensing tube in which I could fit the lens, and then in those regions it behaves like a point-like lens. But then there may be other regions where the lens is just bigger than the Einstein tube or bigger than the Einstein radius. The lensing tube or the Einstein radius, right? In those regions, the mass is distributed so diffusely that it may not be such an efficient lens. It may not deflect light so efficiently, right? And then you may not be able to count those as events, those transits as events. So your lensing becomes inefficient with respect to a point-like lens. And then there's the case where your lens is so fluffy that you couldn't fit it into any part of the lensing tube, and then you just don't count it. And none of those transits get counted. Right? Okay. Yeah.
Could you just say again what the tube is in terms
Yes.
of Einstein radii? And then there's a threshold argument you made earlier. Could you just go back over this?
I'll definitely do that. Yes, sorry. Yeah. Maybe I should have been slower. Okay. So first of all, let's talk about the Einstein radius. That's when, so imagine I'm looking at the wall, and then there's something transiting between me and the wall, and I'm looking, okay. So the Einstein radius is the closest approach of light from the source around the lens and coming towards it, right? Now imagine the transit happens at various intervals between me and the wall. At different distances, I would have different Einstein radii, because the deflection angle would be different, these different. distances. And the envelope of these forms a tube. The word tube is misleading. It's actually an ellipsoid. So it's a lensing ellipsoid, I would call it. Okay. And then, okay. Now, suppose I had a transit that happened way over up there. Then there may not be enough deflection, so I might not get a lot of light. And that means the magnification is not that great. But if I'm within the lensing tube, I'm guaranteed to see a big magnification from the source, right? So the boundary between these two is again the Einstein radius. So when the impact parameter is exactly at the Einstein radius, I end up getting a magnification of 1.34. And so in a survey, I would count something as an event. Again, you only do this because of convention, because you want to calibrate against something, and the calibration lens is a primordial black hole, or a calibration lens is a point lens. So yeah, I could have changed this to 1.1 or something, but by convention, this is the Einstein radius of a point lens. Okay. All right. So that's why I also defined efficiencies of lensing with respect to a point lens, because that's the only way you can talk about these things. That's the only way you can count any sort of an event in this system.
But
Yes?
if the lens is half the size of the Einstein radius, won't that change the shape of the light curve? Even though it's
It
less
will
than.
definitely change the shape of the
You
light.
would see that, right? And some of these lenses are, events are.
Yeah, so it's not immediately obvious that you would be able to see that. It depends on the sensitivity of your telescope. But yeah, in principle, there will be a difference in the light curve and you should be able to see that. Yeah. It won't be a nice parabola. It may be something else. Okay. Okay, so size matters. And just to quantify that a little bit, so here's a lens that could fit into the thicker parts of an Einstein tube, a lensing tube, but not into the thinner parts. Now, for the sake of counting events, remember that I'm interested in looking at an impact parameter of the lens where I get a magnification of at least 1.34, right? So that defines my threshold impact parameter. So let me plot that, the threshold impact parameter, in units of the Einstein radius. And remember, in the case of a point-like lens, it's just 1. So let me plot that for a total magnification of 1.34 as a function of my distance to the lens. And just for illustration, let me take my lens to be some NFW sub here. Okay? Now, it turns out that if my lens size is like 3 solar masses, 3 solar radii, then and I put my source at 50 kiloparsecs where the large Magellanic cloud is. It so turns out that for a lens of this size, it behaves like a point-like lens. So that in most of the distance, in most of the line of sight, it behaves like a point-like lens. That is, its threshold impact parameter is 1. But for the same mass, I don't think I put the mass in here. The mass I chose, I think, is 10 to the minus 3 solar masses. So for the same mass, if I now make the lens fluffier, that is 100 times bigger, then this green curve corresponds exactly to the picture that I just showed. In the central parts of the line of sight, I get the impact parameter is, the threshold impact parameter is just what you would expect for a point-like lens, which is 1. But near the edges, that is close to your telescope and close to the source, the lens needs to get a lot closer, or the center of the lens needs to get a lot closer to the optic axis before you can count it as an event. And so my threshold impact parameter goes down, right? Now if I make the lens even fluffier, make it 10 times bigger than even that, then it's just a fluffy lens for the entirety of the lensing tube. And that means I need to get even more closer to the optic axis before I could count it as an event. So that the threshold impact parameter is much less than 1 for the entirety of the line of sight. Okay? So this is all the information that I need to set constraints, right? I just need to know the effective Einstein radius for a particular lens. That's what this is. The impact parameter at which my magnification is enough to count it as an event. Yes?
So you're assuming these are NFW, White profile substructure.
Yeah.
What's the concentration parameter? I mean, is it something crazy?
It is crazy. So yeah, so for a 10 to the minus 3 solar mass and this size, the concentration parameter I believe is like 10 to the 7 or something.
Yeah, okay.
Yeah, yeah. So this is not motivated by cold dark matter at all.
Okay.
Yeah. Just being agnostic to that.
But the profile, you just chose the profile for convenience.
That's right, that's right. We just, yeah. This is just for illustration, but eventually I'll show you the results for a bunch of different profiles. Yeah.
So if you have such a highly concentrated object, couldn't you argue then that there's a core part that actually, like the core part of the structure would actually fit into your lensing tube? And
Yeah.
so you have like a secondary effect where the inner part lens is different than the outer?
So that is absolutely right, and that's exactly what I'm going to be talking
Great.
about next. Yeah. Yeah. The mass distribution certainly matters in lensing case. Any more questions? Okay. Okay, so so just from the point of view of the size of the lens, we are now in a position to guess how the limits of a microlensing survey would look like in the plane of the size of the lens and the mass of dark matter, or the mass of the dark matter structure. As I was saying, if the mass is too small, then beyond a certain mass, you won't be able to probe the structures with microlensing because the transits are just too brief. The dark matter just flies too fast because the lensing tube is too thin. And above a certain mass, since the number density of dark matter goes as 1 over the mass of dark matter, and since we only know the energy density of dark matter, we know that above a certain mass, all these dark matter structures should be so dilute that you just don't see them. So they're just too rare. But also the fact that above a certain mass, the Einstein radius is so big that the dark matter just stays in the Einstein radius so long that you just don't see a magnification for your transit time. So that sets a boundary here. Now down here, you might end up putting too much mass into a certain size of the lens and just make it too compact. It is compacter than a black hole. So obviously physics breaks down below that. So you draw a boundary over there. Above a certain size, as we just saw, you might put the mass of the dark matter in a very large lens and then make it just so diffuse that effectively it doesn't give you any lensing at all. Right? Now, just to ballpark this for existing surveys that I talked about, OGLE and EROS, assuming no backgrounds, assuming 100% efficiency of detection, here's what you would get as a ballpark of the masses and sizes that you could probe. Both for OGLE that looks at the Milky Way bulge and the EROS survey that looked at both the small Magellanic and large Magellanic lobes. And notice that the slopes of these two lines are different because the Einstein radius goes as the square root of the mass, right? Because the deflection angle goes as the mass, and then the Einstein angle goes as the square root of that. And then the Schwarzschild radius, beyond which you would make your lens too compact, goes linearly as the mass of the object. Okay, so in the most optimistic scenario, this is the entire range of dark matter structure that you could have probed, but then there are always backgrounds and detection issues, efficiency issues, right? Notice that there's an interesting thing happening at these very small lens scales. So this is the wavelength of visible light with which you are doing all this lensing stuff. Everything that we discussed so far was based on geometric optics. But once you get below this limit, wave optics takes over, and you need to account for diffraction effects and stuff like that. And that, to put a long long story short, that kills the effect of microlensing. Okay, so you cannot think of microlensing below this line.
The units there are meters.
Sorry, say that again.
The units are meters? Is that-
Oh, that's right. Yeah.
Sorry, I didn't get it.
Yeah, sorry, yeah. Okay, but then it so turns out that although OGLE seems to be sitting in this wave optics regime, this is for the most optimistic scenario without foregrounds and with 100% efficiency. It so turns out that OGLE actually doesn't fall into this case. So we are fine. Okay, so much for size. And as Sarah just pointed out, it's not just the size that matters. If you just think about it, actually the distribution of mass in the lens should also matter, right? For instance, a fried egg and a chocolate chip cookie and a donut are all roughly the same size and the same mass, but then the way their internal mass is distributed is different, so that the way they scrunch up space-time would be different, and hence the way they deflect light and do microlensing would be different, right? So we studied a bunch of different density profiles or mass distributions for lenses. So we took, for instance, the density profile of a self-similar subhalo, which goes as 9/4 powers of the radius. And then we took an NFW subhalo, which goes as a linear power of the radius inside some scale radius, and then as a cube of the radius outside the scale radius. And then we took a boson star profile, which Juna tells me goes as an exponential drop-off. She's an expert on quantum stars. And then just for illustration, I'm also taking a uniform sphere where the density is constant up to some cutoff, and then I take it to 0 outside that. Okay. Now let's work out how the deflection would look like for a lens with distributed mass. To do this, first of all, you would use what is known as a thin lens approximation. That is, since you know that the size of the lens is so much smaller than the distances to the lens and the distance to the source, you could basically squish the lens into a pancake and just think of a pancake-like lens passing in front of you. Okay, so you integrate out the z direction is what it is. And then on that pancake, to get the effective deflection angle, you basically integrate over the mass components of the lens. Right. So the deflection angle looks like the old deflection angle that we saw, but then what's going on over here is an effective mass distribution, which is an integral over the surface density, the mass surface density of this lens that you got by projecting a spherical lens onto a thin lens. Okay, so when you do that, the lensing equation gets modified. You can generalize it to a distributed mass lens, and the lensing equation now looks like this. This is the angle subtended by the impact parameter, angle subtended by the image, Einstein angle subtended by the image now downstairs, and now you get this extra term, which is the distribution of the enclosed mass normalized to the total mass. Okay, and just to orient ourselves, for a point-like lens, this is 1. Right, all the mass is just inside the point, and outside the point it's 0. Okay, so once we have the lensing equation, we can work out the magnification, and once we have the magnification, we know how to count events, and we get constraints. So let's try to do this for the simplest case that you could think of, a uniform sphere lens, where the density is constant inside and 0 outside. When you turn the crank and try to get what the enclosed mass distribution is, it looks like this on the plane that you project onto, the lens plane that you project onto. So it looks a little complicated. So it looks like a quintic, right? When you put it into the lensing equation, inside the sphere, and then it's just one outside. That's the enclosed mass, right? Okay. So even a simple case such as a uniform sphere, when you try to turn it into a threshold impact parameter, becomes a complicated story like this. Okay. So again, on the x-axis is on the y-axis is the threshold impact parameter at which my magnification is 1.34. That is, it helps me count whether what I'm seeing is an event or not. And then on the x-axis is the size of the lens as a function in units of the Einstein radius. Okay. Now, at very small sizes, if the uniform sphere I'm thinking about is very small, then obviously it behaves like a point-like lens. And a point-like lens produces two images, and both of them contribute to the threshold impact parameter, and then you get that to be 1, as you would expect for a point-like lens. But then, if I make my sphere like a 10% the size of the Einstein tube, the maximum size of the Einstein tube, then the lensing equation becomes complicated enough, because what I have here is a quintic equation. So a quintic equation could give you either 5 solutions or 3 solutions or 1 solution. It so happens that it gives you 3 solutions, 3 real solutions and 2 complex solutions, and then suddenly you have 3 images. And all 3 images contribute to the magnification to get it to above 1.34. And that gives me a spike. And then I make it a little bigger than that. It turns out that you're back to 1 image, because again the quintic just changes its character. And so when the 3 images merge into 1 image, you get a bright peak exactly at that point, and it's known as a caustic. So if I were to draw this for a magnification of say 1000, then none of this curve would exist, but there would be a point exactly at this size up here contributing to the threshold. So you get a caustic feature. All right, so you get, now you only get 1 image, and that image turns out to look like a point-like solution. And then for a while, as I keep increasing the size of the sphere, it behaves like a point-like lens and just sits around at a low threshold parameter. The threshold parameter is lower than 1 because there's only 1 point-like image that tries to contribute to 1.34, and so I need to get the lens as close to the optic axis as possible. And then it turns out that once I raise the size of the sphere above the Einstein radius or above the lensing tube, I'm suddenly getting a spike in the magnification. And that's because now, so the lensing tube is like this big, the sphere is this big. I don't need to get the sphere entirely, I don't need to get the center of the sphere entirely into the lensing tube to start getting magnification. Because most of the sphere is already in there, right? It's a little counterintuitive, but yeah. So I can be far away. I can have my sphere's center far away from the optic axis and still get a magnification of 1.34. But you don't enjoy this for a long time. You make the sphere even bigger than that. At this point, your mass becomes too diffuse, and then you lose efficiency in lensing, and it goes back to zero. Okay, so even a uniform sphere gives you a non-trivial story as far as counting events goes. So as I was saying, the key here is to turn the density profiles to enclosed mass profiles, which we did for these 4 kinds of subhalos, or 4 kinds of structures: the NFW subhalo, the self-similar subhalo, the boson star, and the uniform sphere, which you can turn again into these threshold impact parameter plots as a function of the size of the lens. And each of these has its own story to tell, like the story I said for uniform sphere. The one thing I would like you to notice is that for a boson star, the threshold impact parameter curve looks a lot like the uniform sphere curve. There are two bumps, and there is some time spent by the impact parameter being below 1, right? And that's because a boson star is an exponential drop-off, and that looks more or less like a uniform sphere, right? Like here. So this is a uniform sphere, not very far away from what an exponential drop-off would look like. The other thing I would like you to notice is that an NFW subhalo, you can make it really, really big, but then it would still be a nice and efficient lens. That's just because even if you're above the scale radius, there is still a lot of mass in the subhalo. So that you can be at a very far, your impact parameter can be as far away as possible, but still a lot of mass is within the lensing tube, and you count it as an event. Okay.
Does that ever go away, or does it not go away because there's just a 1/r increase in the density that takes the center of the
I didn't plot it, but then it does go away actually. It's just a linear relation. So after 2 more orders of magnitude, it kind of goes away. Yeah. Oh, you mean this behavior? Yeah. The slope doesn't go away. Yeah. The behavior doesn't go away.
Yeah.
Yeah. Okay. Now we are ready to turn all this into constraints on these various halos. So for a self-similar subhalo, or for that matter any kind of subhalo, as long as the lens size is below 0.1 solar radii, OGLE probes it as though it's a pointless lens. Okay, which we kind of see from here. Up to 0.1, everything looks like a pointless lens. And EROS, for EROS, it turns out the threshold for Einstein radii is bigger, so that lenses that are smaller than 10 solar radii would still look like pointless lenses. Now, if I raise the size of the lens to 1 solar radius, then for a self-similar subhalo, OGLE would be slightly insensitive. Sorry, OGLE would be insensitive to a slightly small region on the left edge of the point. Right. And then if I make the lens 100 solar radius, then EROS would also start losing sensitivity. And basically it would just not become sensitive to the smallest, the lightest lenses. And if I raise these lens sizes 10 times more, then these are the constraints that we would get. Okay, so just keep losing sensitivity as you raise the size of the lens for this particular mass distribution. If I change the mass distribution to an NFW subhalo, because an NFW subhalo is a very good lens, you don't lose sensitivity that easily. So that if I raise the size from like 0.1 to 10 times that, I'm basically not losing any sensitivity at OGLE. When I start making it 10 times more than that, 10 solar radius onwards, do I actually start losing sensitivity? And a similar story for EROS, the sensitivity loss is very slow. And for a boson star, this is how the plot looks. Again, because now you have sharp drop-off, you raise the sensitivity you start losing sensitivity very quickly as you keep raising the size of the lens. Okay, so these are our money plots. Maybe there's a better way to present them, but yeah. Now I would like to end my talk with a very interesting effect in microlensing that I did not mention at all so far, which is that the sources that you're looking at, the stars that you are trying to magnify, actually they're not point sources, right? They actually have a finite size. And the finite size of the star, depending on where your lens is in the line of sight, may actually hurt your lensing efficiency. that you can see from this little cartoon that I drew. If your lens is closer to the star than to you, then the Einstein angle or the Einstein radius is small over there. But also the angle subtended by that is small. By the lensing tube is small compared to the angle subtended by the star itself. In that case, you're not going to get a lot of light reflected from the star coming into your telescope, and that hurts your lensing, right? So I talked about the constraints from EROS and the constraints from OGLE, which are not on this plot. But there's also another leading leading survey called Subaru on Mauna Kea, Hawaii. And they were able to set constraints at even lower masses because they were looking at transit times of like minutes to hours. Now, at first, this was the constraint that they drew without taking into account the finite source effect. And then a bunch of people wrote to them reminding them of this effect. So they changed their curve to this by putting in all sources in the star field they were looking at, which is the Andromeda galaxy. They put all the sources at 1 solar radius and were able to get a constraint that is much weaker than what you would get if you just had point sources. Okay. Now that was not the end of the story. To simplify their analysis, they just set all the stars to 1 solar radius, but Stefano Profumo and collaborators pointed out that actually the distribution of stars in Andromeda across stellar sizes looks like this. That they're not all on 1 solar radius. Actually, most stars are at like 12 solar radius and so on. Okay, so is it time? Okay, so folding in the actual stellar size distribution in Andromeda, Profumo and others were able to set even more weaker constraints, even more accurate constraints that weakened the previous constraints set by the Subaru collaboration by up to a factor of 1,000. Okay, so these were the older constraints, but this is the more accurate constraint. So the lesson here is if you're thinking about lens masses smaller than 10 to the minus 7 solar masses, it turns out that the finite source effect would kick in, and that is something that you cannot escape from. Now, the finite source effect has been worked out very meticulously for point-like lenses, such as primordial black holes and MACHOs. And the key here is trying to derive what the magnification, the new effective magnification is when you put in a finite source. And the magnification looks something like this, which I can explain later. And these guys didn't even have mathematical background, right? So they say, after some tedious algebra, we obtain the magnification as this, with all these incomplete elliptic integrals and so on. So that's been worked out. But if you combine a finite source and an extended lens, we have no idea how the magnification looks like. That's a very, very hard problem. Because now you need to take into account, you need to integrate over the mass distribution of the star and the lens. I don't even know exactly how to set up a lensing equation for that, leave alone calculate the magnification. And I think the way to go is to do this numerically. And unless we have this, there's no way to set constraints for these extended lenses at lower than 10 to the minus 7 solar masses. So that region is still open. Okay, so that's what we're working on right now. So watch this space. All right, so that brings me to the end of my talk. As I was saying, there are non-standard cosmologies where most of the dark matter could be subhalo structures. If so, and if they are in the mass range of an asteroid to the sun's mass, then the best method really to find them today is through gravitational microlensing. And the effect of the microlensing is sensitive to both the size and the distribution of mass, given a mass for the lens. And using the constraints using this probe, and also using light probes, you should be able to tell what the microscopic model is that gives rise to these lenses. And finally, the finite size of the source itself could really weaken your lensing efficiency. Nobody has worked this out for extended lenses. That's something that will. Thank you.